In 2.5, we're going to look at doing another application of determinants, and that's in using determinants to solve systems of linear equations, where A is our coefficient matrix, B is the vector of the constants that are on the right side of our equation. So before we give what Cramer's rule is, let's call the determinant of A D. Let's call A1 a matrix where we replace the first column of A with B. So the first column would be B1, B2, B3, and then the rest of these, A first row, second column, A first row, third column, so forth. Second row, second column, second row, third column, so forth. A2, we would just replace the second column with B. So we would have all other elements would be the same as A. We're just replacing the second column with whatever B is. And so forth. So then D1, we'll just call the determinant of whatever A1 is. D2, the determinant of A2, and so forth. So if we have, using those definitions, if we have this linear system of equations, if we want the value of x sub 1, so our first variable, we take D1 divided by D. So the determinant of A, where the first column is replaced, divided by the determinant of A. X sub 2, that's D2 over D. X sub 3, D3 over D. And as many variables we have. So if we can calculate these determinants, then we can come up with our solutions to our linear system of equations. Now this works if the determinant of A does not equal 0. Notice if we have a 0 for D, then that's undefined. A couple notes there. So if the determinant of A is not 0, that means A has an inverse. That also means there's a unique solution to our system of equations. If D is 0, then there's no inverse and there's not a unique solution. So let's look at an example. Let's start out with a 2 by 2. Let's suppose we have this system of equations. Then D, I guess we need to list A first. A is our coefficient matrix, so 3, -1, 4, 2. B is our vector 0, 5. So D is the determinant of A. So 6 minus -4, so that's 6 plus 4, so that's 10. We have two variables, so we need D1 and D2. So D1, we replace the first column of A with B, so the first column becomes 0, 5. The second column stays the same. So that determinant is 0 minus -5, or 5. D2, we replace the second column with B. So the first column stays the same. The second column becomes 0, 5. So that determinant is 15 minus 0. So 15. Now that we have those determinants, our x of 1 is d1 over d. So 5 over 10, or 1/2. X of 2, that's d2 over d. So 15 over 10, or 3/2. So x, 1/2, 3/2. So x of 1, x of 2. So we want to check that real quickly. If we substitute a 1/2 in, 3 times 1/2, come over on the side, that's 3/2, minus halves, which is 0. If we substitute a 1/2 in here, 4 times 1/2, that's 2, plus 2 times 3/2. The 2's cancel, so 2 plus 3 is indeed 5. So yes, that is indeed the solution to our system of equations. That works out very well for a 2x2 because we can calculate those matrices very quickly, and that keeps us from having to row reduce that system of equations or find the inverse or do things such as that. Let's do another one. Let's suppose we have x of 1 plus x of 2 plus x of 3 equals 8, or x of 2 minus x of 3 is negative 2, and 3, negative 1, 2 equals 0. So our A is 1, 1, 1, 0, 4, negative 1, 3, negative 1, 2. B, 8, negative 2, 0. So D is the determinant of A. So if we want that determinant, we could expand it about a row, or we could row reduce it, either one. Or we could do a combination, I guess. Let's take A. Let's come over on to the next page. So let's begin by doing 3. Let's see, if we want a 0 here, we could do negative 3, row 1, plus row 3 to give us our new row 3. So we have 1, 1, 1, 0, 4, negative 1, negative 3 here, that's negative 3, and 3 is 0, negative 3 minus 1, that's negative 4, negative 3 plus 2, that's negative 1. We can get a 0 here easy enough, so let's let R3 become R2 plus R3. So that would make our new determinant. If we add these together, we get 0. Add those, we get 0. Add those, we get negative 2. So the determinant of A, so that's equal to the determinant of A, even though that's not matrix A. If we multiply down our diagonals, since we have an upper, 1 times 4 times negative 2, we get negative 8 for D, which is the determinant of A. So negative 8. Then A1, let's come back, take those out. A1, we're replacing the first row with b, and b is 8, negative 2, 0. So this time let's just expand across this row. So if we want D1, we want that determinant. So if we expand this way, it's 0 times, cross out row and column, then it's negative 1, except keep in mind this is positive, negative, positive. Row 2, column 1 is odd, so negative, positive, negative. Row 3, column 1, 3 and 1 is even, so positive, negative, positive. So for this one, we use the sign. This one, we use the opposite. So the opposite of negative 1 is positive 1. We cross out row and column. Then we use the sign. So the sign here is 2. Cross out row and column. We get that. 8, 1, negative 2, 4. So D1, we get 0. We get 1 times negative 8 minus negative 2 plus 2 times 32 minus negative 2. So negative 8 plus 2, that's negative 6. 2 times 32 plus 2, 34. 2 34s is 68 minus 6. So for D1, I get 62. So D1, we get 62. We also need D2 and D3. So D2, let's change this back to A. So if that's A, D2, we're going to replace column 2 with B. So 8, negative 2, 0. Let's see, if we could get, it doesn't matter, let's do this one by row reduction. So let's do minus 3, row 1, plus row 3 to give us our new row 3. So 1, 8, 1, 0, negative 2, negative 1. If we do negative 3 plus 3, we get 0. Negative 3 times 8, that's negative 24, 0, so negative 24. Negative 3, 2, negative 1. That doesn't change the value of our determinant during that elementary operation, so if we can get a 0 here, we can use our diagonal product. So if this is a 24, that would cancel. So to make that a 24, multiply, we're going to take negative 12 times row 2. Negative 2 and negative 12 is positive 24, which will cancel. And that's added to row 3. Negative 12 times 0, so 0 plus 0 is 0. 24 minus 24 is 0. Negative 12 times negative 1, that's 12 minus 1. So we're upper triangular, so multiply down the diagonal. So 1 times negative 2 times 11. So negative 22. And that's, instead of being A, that's A2. So the determinant of that, D2, is negative 22. one more, we need D3. So if we get rid of this, that's A. So if we want A3, we replace the third row with B. Let's see, however we want to calculate that determinant. Just for practice, I guess we can go across that row. I'll tell you what, instead of going across that row, let's go down that column. So keep in mind the signs that accompany our cofactors. So if we want that determinant, it's 1, use that sign, times the determinant, cross out row and column. And let's go ahead and multiply that. That's 0 minus 2. So negative 2. We do the opposite. Well, the opposite of 0 is still 0. Just for practice, cross out row and column. That's 0 minus negative 8, so plus 8. Then 3, we use that sign, so plus 3 times, cross out row and column, negative 2 minus 32. Negative 2 minus 32, that's negative 34. So for D3, we get negative 2, 0, and negative 102. So D3 is negative 104. So it's all over but the crime now. So we want x1, x2, and x of 3. So x of 1 is D1 over D, which is 62 over negative 8. That reduces a little. It's negative 8 doesn't go into that, 4 doesn't go into both, but 2 goes into both. So negative 31 over 4. X of 2, that's D sub 2 over D. So negative 22 over negative 8. 2 negatives make a positive. 2 goes into each of those, so 11 fourths. And x of 3 is D3 over D. So negative 104 over negative 8. Let's see. Four goes into both of those. Negative over negative makes a positive. 4 goes into 8 twice. 4 goes into 10 twice. With 2 left over, 4 goes into 24 6 times. And I believe that's 13. Let's see, 8 goes into 10 once, with 2 left over, 8 goes into 24 3 times. So yeah. So x1, x2, and x3. And if we just check, we won't take time to check all 3 equations, but if we do the top one, negative 31 fourths plus 11 fourths plus 13, that's negative 20 fourths, which is negative 5. Negative 5 plus 13 is 8. So yeah, that works. We do the second one, 4 times x of 2. This is x of 2, so 4 times 11 fourths minus x of 3. 11 minus 13, yeah, that's negative 2. And I would suspect it also works for the third one. So those are both good illustrations of Cramer's rule. If we can figure out d, d1, d2, d3, d's for each variable, then our value is just the corresponding d divided by d in general. So x1, d1 over d, x2, d2 over d, and so forth.